Okay, great. I believe we are live, and I'm asking people on YouTube, if you're streaming in, to just send something in the chat that says you can hear us. I'm sharing the agenda both in Zoom and on the YouTube. And this agenda is largely divided into two elements. First, we're going to go over just general sharding design and some of the awesome cryptographic primitives that are used in this design with Dankrad and Vitalik. Then we'll have a short break, and then we're going to go over kind of the current vision, state of prototyping, and separation of concerns, and the Eth1+Eth2 merge. I'll give a little bit of an intro there, then Mikhail and Guillaume are going to take it over. There's a few goals of our workshop. The first and foremost is to educate on these two kind of large upgrades of the beacon chain that we expect to happen over the next couple of years, to facilitate more collaboration and development on it. Pretty much the beacon chain is launched. There are a couple of big things that we want to do with it. One is for it to become the new home for Eth1, Ethereum, and to facilitate some massive scale through what we call sharding. Both of those are kind of on the cusp of R&D entering into the D side. It's definitely time to get more engineers, more minds to refine specifications, get prototypes out, and ultimately bring these things to mainnet. So that's our goal today, is to kind of expand who's aware of these things, who's involved with these things, and facilitate a really exciting year collaborating on both. So I need to give Xiaowei host permissions. Give me 1 second. Great. So that is done. So this is going to be a mix of presentations that people prepared to help educate, but in the nature of like a workshop, in the nature of an educational thing rather than like some sort of conference, I hope and have encouraged speakers to pause, ask if there's questions at various points throughout, so that we can more dynamically engage with the information. And part way through some of the sessions, and definitely after each of the sessions, open it up for more general conversation. But don't be afraid to like raise your hand, drop a question in the chat, or wait until one of those moments when the speakers ask if there's any questions. And if there's not any questions, I'll probably ask questions to keep this thing moving. Cool. So I think that's all in terms of the structure of today. It'll be a mix of presentations, some dynamic discussion, and otherwise, thank you everyone for coming. I'm sorry that we, again, are all hanging out on the internet rather than in person, but it's really, really good to see everyone show up and see all these nice faces. With that, I'm going to turn it over to our first part one of today, the sharding design and the cryptographic primitives. I believe, Dankrad, you're going to start us off, right?
Mm-hmm.
Okay, turn it over to Dankrad. Thank you.
All right. Thanks, Danny. I will share my screen. Right. Can you all see my screen?
Yes.
Yes. Okay, great. Thanks, Danny. So I am mainly going to talk about KZG or Kate commitments, because that is an essential ingredient on how we're going to design sharding in Eth2. And basically, the way to think about it is, I gave the subtitle, how to hash polynomials. Right, so this is the outline of what I'm going to talk about. I'll start with some motivation, why in data availability sampling we need polynomial commitments, why they're useful. And then I will quickly go over finite fields, just so that anyone who is not completely familiar with it kind of knows what we're talking about. And then I will talk about basically a simple construction that you could think about to hash polynomials that is broken in some way, but very naturally leads us into KZG commitments and proofs. And then finally, I'll give a quick overview of like where you can go from here and continue. And please feel free to ask questions at any time. This is like for your benefit to understand it. So if anything's not clear, please just ask about it. All right, let's start with the motivation. So data availability sampling. The basic idea is you have got this blob of data that would be a block on an Eth2 shard. And you want to be sure that the data is actually available without downloading the whole data. Obviously, like when you can download data, then you know it's available, but that's a bit too much work. So we want to do this by only sampling some part of the data, by doing random sampling of data chunks, basically. And the advantage of doing this is that this does not depend on the honest majority. So for example, an alternative data availability solution is you send a committee to download the full data, vote on whether it's available. That's actually what we're going to do as well. But the problem is that only works if that the majority of that committee is honest. And that again only works if, as a very minimum, the majority of validators is honest. And data availability even works, like data availability sampling even works when that is not the case. In order to be able to do this, we need to do some encoding of the data, so-called erasure coding. Because if you just sampled the data itself, the random samples, then it's if an attacker is, say, just hiding one of the chunks, it's very unlikely that you're going to hit that one. So it's easy to hide small amounts of the data, and we want to avoid that. Okay, so how does erasure coding work? We say we extend the data using a read Solomon code, which is a fancy name for polynomial interpolation. And what we do is we take the original data. So I like four chunks I've drawn here, and then you find a polynomial, well, the polynomial that goes through all those chunks of minimal degree. So in this case, since it's 4 chunks, that would be a polynomial of degree 3. Ignore the 5 here, that's somehow from an old slide. So the polynomial would be of degree 3. And in this case, since we know that we can always find with any 4 samples of or points of a polynomial of degree 3, we can always find the polynomial. We know that any 50% of the chunks are going to be enough to reconstruct the whole data. So it doesn't matter which one we have. We can have 2 original data, 2 extension, or all extension, anything, all of them, no matter what you get in your sample. If you have 50%, you can reconstruct it. And so now we have changed the game. Like basically now we only need to be sure that 50% of the data is available rather than that that everything's available. Because we know if it's 50%, if 50% of the extended data is available, then that's enough, right? And now that problem you can solve using random sampling. You've converted it into a problem that random sampling can do, because if you take 30 samples, and if all of them are available, then the probability that less than 50% is available is very, very low. Right.
Fun fact,
now,
erasure coding is how they do make CDs skip resistant.
Yep, that's right. Okay, so let's now think about, like, if we just committed to the Merkle root of this data and extension, right? Then there's one problem. Like that would be the natural thing to do, right? That's how we usually commit to large amount of data. We commute the Merkle root. But the problem is, how do we know that the data and the extension are on the same polynomial of degree 3 in this case, right? So here we illustrate what happens. We have like the original data and the polynomial extension, but this attacker, they just make up anything for the extension, right? And then you can't reconstruct the data from the extension because it's a completely different polynomial, or like the whole thing is not any sort of low degree polynomial that can be extended from a small number of samples. So what we would need is, if we did this using Merkle roots, we would need to introduce a fraud proof in case it's incorrect. So someone would have to collect enough data and send it to everyone to show that someone distributed the incorrect root. And the downside of that is basically that fraud proofs add complexity to the protocol, obviously, but also more annoyingly, they add these synchronicity conditions that, like if you have poor networking or anything, like you might miss the fraud proof and therefore think that the wrong chain is valid. So the question is, what if we could find a kind of commitment that always commits to a polynomial? That would be great. Then we wouldn't have that problem. Okay. Now I'm going to talk a bit about finite fields because we need them, and I'm not sure if everyone is completely familiar with them here.
Maybe are there any questions on the previous stuff before we move on?
Yep, sure. Happy to take any questions.
Could you use a zero knowledge proof to prove that it was a polynomial extension?
Right. So this would be another possibility. We could construct a zero knowledge proof, so we could compute this Merkle root, and then we could afterwards, since this is just a computation, right? The input is all the data and extension elements, and for example, in addition, you could give the polynomial, like the coefficient of the polynomial that they're on, and then inside the zero knowledge proof compute this root. So that's possible. It's just that it's currently computationally infeasible. Like it would be a lot of work that just realistically can't be done in the space of time.
Right. In a few years, it'll get easier once we have more established arithmetically friendly hash functions. So, I'm definitely expecting that in the longer term, it will be easier to have snark silver Merkle roots and eventually Stark silver Merkle roots. And once quantum computers come out, that's something we'll have to switch to anyway.
Yeah.
I mean, one thing I was wondering about was what's the thinking with regards to an interactive protocol versus just broadcasting the information, for example, similar to how we broadcast stations.
Oh, you mean an interactive protocol for data availability?
Yeah.
Well, it's very, very difficult to do. Well, it's impossible actually, because the problem is you can never prove that data is not available. Like you can always, whenever someone challenges you, hey, this data is not available, you can just show it and say like it's here all the time. It was here all of the time. You can't prove that it wasn't there, basically.
And if it was in terms of the like dynamic requests for sampling versus sampling on broadcast, Vitalik is, I think, going to cover that in his portion.
Right, but that is a good point. Yeah, like I mean, you can always like, it's basically probably like very intuitive that you think, oh, it's just like this challenge response thing, but there is actually not really any solution in this space for data availability.
I think for an intro, maybe you can explain why we need this for Ethereum 2 and not, we don't have this for Ethereum 1.
Well,
Well,
the
actually-
explanation for that was going to be the first slide of what I'm presenting on.
Okay,
So,
then I will.
Yeah,
I will
maybe
leave
let
that
let Dankrad talk about theory, and I'll talk about sharding.
Let's do that. Great. Cool. Okay, let's get into finite fields, right? So I could give a very mathematical definition, but I don't think that's very useful. I think the best way to think about finite fields is, you all know the rational numbers, usually denoted by this double bar Q, or the real numbers and the complex numbers. And we all know that we can do basic math operations with them. Like we can add them, we can divide, subtract them, we can multiply them, and we can divide except by 0, right? There's always one element and exactly one that we can't divide by. And that's it. Well, otherwise we can always do these. And then they are like the basic laws, associative, commutative, and distributive. And I don't need to go into these, like, just think about like you have the same laws as if you were using rational numbers. The difference is that they're finite. So unlike the rational numbers and all the others, they all have an infinite number of elements. And finite fields only have a finite number of elements. And that is important because that means we can actually represent them all using the same number of bits. Like if the, so for example, for the modulus we're using in the elliptic curve in BLS 12381, it's always 255 bits. Whereas a rational number, for example, could grow very, very large. If the numerator and denominator, they can both be any integer, and we know that we can't represent all integers using a finite or the same finite number of bits. They might have to grow. And then the best way, I think, is like to just look at an example. So I'm going to look at F5, which is basically the finite field that consists of the numbers 0, 1, 2, 3, and 4. And the idea is that for every operation that we've talked about before, to compute the result of the operation, we first just compute it using integers, and then we take the remainder after division by 5, and this remainder is the result of our computation. So for example, if we do something like 3 plus 4, right, then that's 7, and 7 divided by 5 is 1 with remainder 2. So we say that that's 2. Like in our field, we say the result of that is 2. And then do another example, like 3 times 3, the result is 9, and modulo 5, the remainder modulo 5 is 4. So we say that that is 4. And now there's one thing missing. If you divide, obviously you can't do division in the integers generally. And the way you do that is basically, I've made a little table here that shows that for each element 0, 1, 2, 3, 4, you can find an inverse. An inverse means that if you multiply it by that element, so for example, for 2, it's 3, then you get 1. So 2 times 3 is 6, and 6 modulo 5 is 1. And the division basically just works by multiplying by that inverse. So for example, now if I wanted to divide 4 by 3, then I would do 4 times the inverse of 3, which is 2, which is 8, and so the outcome would be 3. And that works because 5 is a prime number, basically. If it's a prime number, then we can prove that there's always an inverse. Like each of the elements will have an inverse. Otherwise, that's not true. Right. And we can do this for any prime. So this is just an example to show how it works in a small field. But in practice, our primes are going to be huge. Going to have hundreds of bits. Okay. Based on this, I'm now going to talk about hashes of polynomials. First, a quick reminder about polynomials. So a polynomial is an expression of this form. So it's the sum of some fi, which we call coefficients, times x to the power of I. And we call these fi, as I've just said, the coefficients, and the degree is basically the highest coefficient that we have in the polynomial, so n. And each polynomial defines a polynomial function. That's basically the function that's defined when you replace this x by values in the field. And then just some facts from basic math. So for any k points, so if you're given k pairs of values, x and y, where all the x are different, then we can always find a polynomial of degree k minus 1 or lower that goes through all these k points. And any polynomial of degree n that is not constant has at most n zeros. Okay, these are some basics about polynomials. And what we would like now is to have some kind of hash function for polynomial. So it's a hash function that takes as an input a polynomial f. And what would be great if it has some extra functionality. So what would be nice is if for each z, so the z is some element from our finite field, you could construct a proof p of f and z that proves that h of z is equal to y. And the proof, as well as the hash itself, would ideally be small. And here's an idea for such a hash function, which I call random evaluation. So let's choose some random number. Let's say, so we're still working in F5 right now, just as an example. And let's say our random number is 3. And now I say, to hash a polynomial, I evaluate it at this random number. So I've given 2 examples here. Like I take f of x, which is x squared plus 2x plus 4. I compute what that is. If I evaluate that modulo 5, and you get that it's 4 in this case. And that's another example for another polynomial. So basically, you just compute the evaluation. And now, I mean, okay, so like, I mean, we only have 4 possible outcomes in F5, but if we said the modulus had 256 bits, then it's actually super unlikely that 2 polynomials would have the same hash, right? Because there are so many possible numbers. Like 2 to the 256 is so many, it's very, very unlikely. And this trivial function has actually some very nice properties. So for example, here I give like the first one, h of f. So if I add 2 hashes, h of f plus h of g, that's the same as if I first add the 2 polynomials using normal polynomial addition, and so that has the same hash. And that's because if we just take f at 3 and add g of 3, like 3 is just my example here for a random number, then that's the same as if I add f plus g and then evaluate that polynomial at 3. It's really like a completely trivial statement when you think about it. And exactly the same is true for multiplication, right? If we like multiplying two polynomials is again exactly defined in such a way when you write it out, just doing the term by term multiplication, so that h of f times h of g equals, oh, that should be an h here, h of f times g. And that's again because when you just write it out, what it means to actually evaluate a polynomial at a point, then f of 3 times g of 3 is obviously f times g evaluated at 3. Okay, so it looks like this idea has some fairly interesting properties. So that's nice. But the problem with it is that you can very easily create a collision if you know the random number. Like if you know that I'm going to evaluate it at a certain number, then if it's adversarial, like before we just assumed like, oh, it's just random polynomials and that works very well. Problem is if it's adversarial, if there is an adversary who tries to create a collision, then they can very easily do that. Because like they can just modify, for example, the constant term so that the two polynomials have the same hash in this case. So what we actually want is some way of instead doing this inside a black box. What would be nice if we can put a secret number, which I call S here, S for secret. And we could put it into a black box. So I denote this black box by the square bracket here. And let's add also into black boxes the powers of that number. So s squared, s to the power of 3, and so on. And in such a way, ideally, like this is all kind of just imagining how nice it would be if we could do that, so that we can multiply it. This should be by a field element, by a scalar, and add. So I'll do correction on the slide. Multiply it with another number, so that it should be possible, and add two of them. But what we don't want is that you can multiply two numbers in the black box. So so what you want is, for example, that you can do some a times s, which would go into the black box, so that this is kind of as. And what would also be nice if you can do like s plus s squared. So that you can create another black box that has s plus s squared. So those are good. What would be bad is if we could do something like take two black boxes, s times s squared, and compute another one. And the reason for that, why that is bad, is basically that that if that were the case, then you could compute also the inverse of s. Then you could compute in some ways using many operations. You could get to compute s to the power of -1. And once you have that, then we're screwed, because then you can use this not just for polynomials, but also for fractions. And we don't want fractions of polynomials. We only want polynomials. Okay, so that would be, yeah.
I was just going to say it's actually even worse because I believe you didn't use fancy elliptic curve algorithms to discover what f is, if you can multiply.
Right. I probably, yes. Yeah. Cool. So that's kind of what we would like to have. And the great thing is that very surprisingly, elliptic curves are the rescue here. They provide exactly that. So this is actually how you should think in the future of an elliptic curve. An elliptic curve is a black box for one of these finite field elements. Each elliptic curve has a curve order. So I call it G1. The reason for the 1 here will be apparent a bit later because we will need another group, G2. And we say there's a generator, which is basically one of the elements in there. And the order is P. Order means that P times G1 is basically is 0. And to represent any field element inside in FP, you multiply the generator with X, so X times G1, and you can multiply. So G is now here the G, so G1. This is like any element in the group, and so is H. So you can compute X times G for any element. You can add 2 different elements, like if G is an element and H is an element, you can add G plus H, and you can compute these linear combinations, X times G plus Y times H. But this is the thing you can't do. You cannot compute G times H. You can't multiply 2 of them. And we introduced this notation where we inspired by the black box, so square brackets. We just add the 1 here, which means that it's in this G1 for X times G1. And that's our black box. So basically, elliptic curves are just black box finite fields. Okay, and then we are ready to introduce KZG commitments. Okay, so here, here's how a KZG or KT commitment works. So we assume that we have this trusted setup. So we have the secret number to the power of I for different I, 0, 1. If it's 0, then it's just 1. So then it's just a 1. Up to some large number. That's the length of the trusted setup. When you have this in 1 and in the second elliptic curve, which I'll come to a bit later. And we take this, which we have a polynomial f of x. And now here's how we compute the KZG commitment. We take the coefficients of the polynomial, and we basically, if you look at this formula, we just replace x by s to the power of I. So x to the power of I is replaced by s to the power of I in the square bracket, so in the elliptic curve. And now when we multiply out this formula, we see we can move those coefficients inside the box, right? We stated before, like we want to be able to multiply something like in the box, a times x equals ax. You can multiply by a scalar. And then we have the sum. We basically just use that x plus y equals x plus 1. And so we can also move the square brackets outside the sum. And then from there, we see that actually this commitment that we can compute like this is just s at the point s inside the elliptic curve. That's all it is. It's just the evaluation of the polynomial at some secret random point, but inside the elliptic curve, and nobody knows what the actual point is. And that's what we call the KT commitment. So basically, we've now transformed our random evaluation scheme that we had before, and that's completely broken. That obviously doesn't work when there's an adversary. And by moving it into this black box world where we can compute with black box numbers in elliptic curves, we've turned it into something that at least gives us a hash for a polynomial at this point. Okay, so that's cool. Now we need to in order to do something with that, we need to do a quick recap on pairings. Okay, so it's a pairing is a function that we usually denote with an e that takes as an input two elliptic curve elements from G1 and G2. And now here is the reason why we have to talk about this G2, because most pairings, or like the pairings we work with nowadays, aren't symmetric. So we need two different elliptic curves for the first and the second element that you put into the pairing. And the output of the pairing, the output of this function, is in a target group GT. So GT is a different kind of group, but essentially you can still think about it as like some group of the order of the finite field. So it's basically just yet another version. Like G1 is some version of the black box of the finite field, G2 is, and GT is a third one. Unfortunately, they all have to be different. I guess like, well, in some ways it would be nice if they're all the same, but actually it would break down if GT were the same. So we need all these different groups. Okay, and the important property of this pairing is that it is bilinear. Okay, what does bilinear mean? It's actually it's very it's kind of bilinear. If you've ever done like a linear algebra course, it's actually exactly what it means, the same as bilinear, only that the notation is very strange, because in the target group, at least, we still denote everything in the exponents, and so it all looks a bit weird, but actually it is exactly what you have learned as bilinear in, say, linear algebra. So what it means, we have this pairing of a times x, so we've multiplied times z, and then we can take out this a, and in this case we put it in the exponent. So that's very confusing, right? What you would expect traditionally from bilinear is that it would be here, then we would all agree this is bilinear, but don't get confused by this. It's actually still bilinear. It's just a strange notation that we use for the target group. And the same is true in the second component. Well, that's why it's bilinear in both components. So like b times z, you can again take the b out and put it into the exponent. And then the same is true for addition. So if we add two numbers, x plus y and z, and paired with z, then we get the pairing of x with z. Actually, sorry, I messed up my notation here. This should be times. In this case, should be the product of the two pairings. Okay. All right. So this that is how pairings in elliptic curves work. Is basically it's a bilinear map on two elliptic curves. Okay. Right. So the cool thing is when you look at that, then pairings allow you to do multiplications. So we have this, we take e of x in a black box and y in a black box, and then just by applying our two equations, so we take first the x out, and what remains is a 1, because we can always say x equals x times 1. So we can take an x out, put it in the exponent. And then we do the same with the y. And now we have computed this x times y in the exponent here. And so now we add the notation for the target group. We add another of this black box notation, and we just, whatever is in the exponents, e of 1 and 1 in the black box, that we denote by this square bracket t for the target group. And then we get the nicer equation. We don't have to write the strange stuff in the exponents anymore, where we get e of x, y equals x times y. So we just multiplied x and y essentially inside the black box. I should probably quickly mention, I said earlier, we don't want that it's possible to multiply. Like, you might wonder now, haven't we just introduced something where you can multiply two of these s, right? Where I earlier said we don't want to be able to multiply two numbers in a black box. It actually turns out to be okay here, because the output is a different kind of number. That's why we need this target group. We don't get a result in G1 or G2, but we get something completely new. And that's why it's okay. All right. So let's assume we have two polynomials, F1x and G of x, and we committed to both of them using Katik commitment. So we have a commitment to F in the first elliptic group, and in G2 we have a commitment. So G of S to G of S we commit in G2. And so we notice that we can, using the pairing, we can compute the product of these two polynomials. So using the pairing, we can multiply two polynomials. Cool. Oh, sorry, same slide. Okay. Okay, so why is this useful? Well, we need one more missing piece. Then we've got what Katik proofs work, how Katik proofs work. So if we have that f of x is a polynomial and y and z are two field elements, then by the so-called factor theorem, it's actually a fancy name for a result that you can very, very easily prove using long polynomial division. If you want to check it, Google it, it's a very easy proof. But basically what it says is this quotient f of x minus y divided by x minus z is a polynomial, right? I mean, it doesn't look like a polynomial at first. It's a rational function, right? It's a division of two polynomials, which we call a rational function. And it's a polynomial if f of z equals y. Okay, and you can restate that another way, like just multiply this equation by x minus z to bring it on the other side. Then there exists some polynomial q of x that fulfills the equation q of x times x minus z is equal to f of x minus y if and only if f of z equals y. Cool, and that's how we get to the KZG proof. So if we want to prove that f of z equals y here, f of z equals y, then we compute this quotient q of x, f of x minus y divided by x minus z, which is a polynomial, as if we are an honest prover that wants to compute an honest proof. So we know this is polynomial, and so we compute this quotient, and then we send the commitment to that quotient. And the verifier then checks that that e of f of s minus y paired with 1 equals e of q of s. So that's the commitment to this quotient. S minus z. If you look at this, that's a commitment to the denominator here, right? x becomes s, that's a commitment to the polynomial, to the denominator. This is the equation that the verifier checks. Okay, and why is this true? Well, so if you look at it, then the right-hand side, it turns out, is a multiplication. It multiplies these two polynomials, as we've seen earlier, right? Using the pairing, we can multiply two polynomials. So we multiply these two polynomials. So what we get is q of s times s minus v. So that is a commitment to the polynomial, right? If we write this as polynomials again, q of x times x minus v. But that's just f of x minus v, right? So if this equation is true, then that's f of x minus v, minus y, of course. Okay, so that's, if the equation is true, then that is f of s minus y. And that is obviously the same as the very first pairing. Okay, I think so. This is really like the core of everything. So I'll pause here if anyone wants to ask some questions. I don't know if that's clear. But so the core of the argument is just if this, like, it's clear that if we can compute q of x, then this proof holds, right? So we can just do the algebra as I just demonstrated, and this thing, two things, the two pairings should be equal. And the other way is like, if it doesn't hold, then the problem is that somehow if the prover wanted this pairing to be fulfilled, they would have to commit a commitment here on the left-hand side to something that's not a polynomial. And they can't do that because we have only given them the positive powers of s. So they just cannot commit to the quotient if it's not a polynomial.
Can I just ask a quick question?
Yes, please.
What do the points in the target group look like? Because I know that the ones in G2 are like a field extension of degree 12 or something, right?
No, they are actually a field extension of degree 2. And the GT are the extension of degree 12. So the second one is an elliptic curve of the over a field extension of degree 2. Right, that's G2. I'm talking about BLS 12381 here. And the GT group is not an elliptic curve. It's simply, it is itself a field extension of degree 12.
Okay.
Cool. Okay. Please ask any question if anything is unclear. This is really like the core of the. If you understand this, then like that's amazing, because then you've completely understood KZG commitment. And if not, you should ask questions now.
Are we the first project to try to use KZG in production?
Well, I would say, I mean, like at least many snarks do use KZG in some way, or like you.
Right, and I think ZK Sync doesn't it already use Plonk, which is based on KZG?
Yeah, so Plonk is definitely based on KZG. I mean, you could even argue that in a way, even Growth 16 proofs, like it's still kind of based on KZG, although it doesn't use KZG explicitly. Like any, all prover schemes that use a trusted setup over elliptic curves essentially are in some sort kind of based on KZG.
So to be clear, T is that element that you need to do the trusted setup for.
S.
S. Gotcha. That's what's in the black box.
So these elements, so the trusted setup are these elements. Oops, where's my pen gone? Are these, right? S,
Right.
S squared, and so on. And T, the GT is just, that's just a group. That's just like that. That's not, that doesn't need a trusted setup. Okay, great. All right. If there are no further questions, then.
So from a practical standpoint, to bring these into production, what are the things that teams need to be thinking about doing, or kind of some expertise that might need to be built around here?
Right. So I mean, I think like conceptually, like the Kate commitment themselves aren't very difficult. Like, I mean, once you have really understood this part, then doing the basics, just checking, say, one Kate proof as it's done here, or computing a commitment, like that once you have the elliptic curve library, which is the hard part, that is very simple and anyone can do that. There are some more things that will need to be built out in the future, but they are more relevant. So actually, like technically speaking, for the very first version of this, the only thing you'll need to be able to do is to compute and check a commitment. So before we do data availability sampling, which we might only do in a future version, in an upgrade, you don't actually need to do anything elaborate. For full data availability sampling, you need to do like many more things, which is like computing these multi-proofs and stuff like that. I think like we should probably have another presentation about that, how to do this, because that is a lot more technical. And yeah.
Would you mind, for those that might be treating this more as like a black box and has certain engineering properties, would you mind just like running over those real quick? Like the size of the commitment, the size of the proof, does the size of the proof scale with the amount of data that you're trying to prove against it, that kind of stuff?
Right. So I mean, this is basically the summary slide. So go there, right? So I'll just quickly go over it. So this is just a recap. So yeah, you commit in the KZG commitment scheme, you commit to any polynomial using a single G1 element. What's a G1 element? So that's like this. If you serialize it, it's a 48 byte blob, basically. That, yeah.
And to take it back to the beginning, commitment to a polynomial was commitment to block data divided up into points.
Right. Yeah. And so when you open the commitment, so points as well as the value, right? These are both field elements. So these would be in the fields. So that's FP. And P has 255 bits, so that's like a 32 bytes. So, 32 bytes. And then the proof for that is again just one G1 element. So again, 48 bytes. So you do not actually need like there's no need to ever send any G2 elements for this.
Right.
And finally, to check this proof, you'd use this pairing equation. So it's a very simple one-line equation. E of f of s minus y paired with 1 is E of the quotient paired with s minus c.
Cool. So we have a 48 byte commitment to a block, essentially, or an extension of a block. And then that block is composed of points, 32 byte points. And I can prove the inclusion of any of those points against that 48 byte root with a 48 byte proof. Is
Yes,
that correct?
yeah. Any of the points you can, for any of the points in that, so you don't need like a Merkle root, like to get to a point, you need this whole branch, right? All the siblings somewhere here in a tree, and you need to give all the siblings in that tree.
Right. And in the context of if I want to prove many points that we're committed to, do I need many 48 byte proofs, or can I just use one?
No, so there are schemes, and I didn't go into that because there are many different schemes, and I don't want to. And yeah, I mean, I think like understanding the basics is the most important here. Okay. But there are schemes where you can take any number of points down here, and obviously you will need all the points and their values. But once you have that, then the actual proof is still only one element.
Okay. Any other questions for Dankrad? I think we're about to move on to Vitalik. And as I mentioned in the chat, we're going from math heavy in the direction of engineering heavy. So if your eyes glazed over on that, I think you'll be able to bite into this next thing. And if you enjoyed that, reach out to Dankrad. I think Dankrad and Proto have a small group of working on some of the practicalities of implementing some of these things and optimizing them. So if somebody on your team wants to dig in deeper, reach out to Dankrad and Proto.
Okay.
And I've collected quickly some reading materials here, but I'll just share the slides later, so you can just take it from there.
Thank you.
Cool. Thanks.
Cool. Okay. Then I guess I will start my presentation. Does everyone hear me and see the slide okay?
Yep.
Okay. Great. So to start off, some key goals of sharding, and this is just motivation for why we need to do kind of any fancy stuff at all in Eth2 when we don't need any fancy stuff in Eth1. So basically, the goal of sharding is that we want to create a system that can process far more transactions, and specifically a system that can process so many transactions that you do not want to require any single node to process all of the data. So one important nuance is that at layer 1, we're doing data sharding only. So which basically means that the sharding is only just coming to consensus on blobs of data and on the fact that blobs of data and specifically about 1.5 megabytes per second worth of blobs of data is available. And it's not doing any kind of execution of transactions inside of shards directly. Right now, you might want to ask kind of what is the point of having this data space? And there's a few applications, like you can store cat pictures on chain. There's enterprise applications that might require some kind of on-chain data storage of different kinds, and then you would just have a kind of separate scripts that would kind of walk over that data. And finally, rollups. Right? So basically with rollups, what happens is that you need some kind of space where data gets published in order to get around the data availability issues and just make sure that the data actually is there, so that other nodes can come in and generate state or generate fraud or generate fraud proofs. And I've talked about this a lot in other discussions and other contexts. And basically, like even though there's no execution sharding on layer 1, with rollups you kind of get execution sharding on layer 2. And if we want, we can add execution sharding on layer 1 at some point later, but that's like not part of this phase of the roadmap. Right. So here, what we're just trying to do is we're just trying to come to consensus on, well, during each slots or during every 12 seconds, blobs of data that get 64 blobs of data, where each blob of data has a size of somewhere between 0 and half megabyte. So we have 64 shards, and it's probably best to just think of these as indices. So think of these as just numbers from 0 to 63. During each slot, for every shard, so for every index from 0 to 63, a proposer gets assigned. The proposer has the right to create the shard block at that shard for that, or at that slot for that shard, and a tester committee is assigned. So basically, the set of validators that are testing at a particular slot are themselves split into 64 groups and randomly assigned to these different shards. If there's not enough validators, then there's the number of shards that actually get a block during a slot get reduced, but that's a detail. Don't need to think about that for now. So basically, what's going on here is that you have these beacon blocks, and then you have these shard blocks, and a shard block has the block body, which is just a blob of data up to 16,384 field elements in size. So that just means up to half a megabyte. There is an EIP 1559 like mechanism in place, so it would be targeted so that on average these things are half full. But basically, their size can be anywhere from 0 to about half a megabyte. But actually, like, this is not bytes, this is field elements, right? So this is a list of numbers from 0 to some really big long number whose digits I don't even remember, but it's somewhere between 2 to the 254 and 2 to the 255, or 2 to the 253, I forget which one. So block body is basically just a list of these field elements, a list of these numbers from 0 to between 0 and p, inclusive on the left side, not the right side. And the header is a Kate commitment to the blob, cat KZG commitments to the blob, a proof of size, so just a proof that proves how exactly what the size of the blob is, which you need for the EIP 1559 pricing mechanism, and the signature from the proposer. Right, so it's a fairly simple structure for a block. You have the body, which is the data, and then you have a header, which commits to the data, and then also just proves how big the data is and adds a signature from the proposer. And the block header, or the shard block header, can get included in the next beacon block or in the later beacon blocks. Now, so shard block structure. So this is the structure of the shard block as it gets sent over the wire. Well, over the wire, you would probably realistically just send the first n samples, and you would send all the proofs. But basically, you have a commitment, which is the cat-say commitment to the entire block. Then you have the actual contents, and you can, if you have the original contents, then you can derive the remaining contents basically by just recovering the polynomial and evaluating the polynomial at some set of standardized coordinates. And if you have any n of these samples, then you can use that to recover the full data. And then here we have, we also have this set of proofs, and these are basically just the quotients that Dankrad talks about. So you have one, now one kind of implementation detail is that instead of having one proof for each single evaluation, you have one proof for each set of like either 8 or 16 evaluations, and like you can do, you can make kind of multi evaluation proofs fairly easily, as Dankrad mentioned. So the thing that would get sent over the wire is probably basically just the first n samples. And from the first n samples, you can theoretically recover everything else, right? From the first n samples, you can recover what the polynomial was that gave these outputs at those coordinates, and then you can compute the commitments, and then you can verify, and then you can generate all the proofs. Though realistically, for efficiency purposes, it might be better to just also provide the proofs as well, because they do take a little longer to generate than everything else. So this would get sent over the wire, and then the attester committee would download this data, and they would verify it. And the attester committee, basically, their job is to vote on which proposal to include, right? So if there are two proposals or more, which only happens if the proposer is malicious, then they vote and they choose one. And if there's 0 proposals, then they just vote for the default 0 proposal. Or if all the proposals that were published are unavailable, which basically means that, like when we say a proposal is unavailable, what we mean is that like the proposal header exists, but the proposal body just can't be found. Then they choose the default kind of 0 proposal, which just means that they just say there's nothing there. And that's always an option that the attester committee has, right? So shard block proposer makes a proposal, publishes it on a subnet, or publishes the body on the subnet, publishes the header on the global net. The header gets included into the next beacon block basically as soon as there's an honest proposer that hears about it. And the attester committee is voting on the fork choice rule, like kind of LMD related stuff and FFG related stuff for the beacon chain, and on shard proposals simultaneously. So we're kind of adding one more responsibility to what these attester committees are doing. Also, we have a kind of fork choice rule change, which is this concept of tight coupling, right? So basically, we have this concept of a beacon chain confirming a shard block. So the concept of confirming basically is that this is kind of the first layer of defense against unavailable proposals being included. So basically, if we have a malicious proposer here and they publish the header, but they don't publish the body, then the attester committee would vote against that proposal, and so normally it would not get included. But if the proposal actually is available, so if the full body can be downloaded, then the attester committee would vote for it. And the critical thing is that the proposal is, or the shard block is considered a canonical part of the chain only when first the proposal is actually included in the beacon, or the header is actually included in the beacon chain, and second when you get votes for that proposal from at least 2/3 of the attester committee to confirm immediately, or you need a kind of majority or a plurality of votes to include it after like about 1.5 epochs. So once the shard block is confirmed in the beacon chain, then you have this fork choice mechanism where basically the shard block becomes a dependency of the beacon block, right? So if it turns out that the shard block actually is not canonical or is not available, then that beacon block is now just not able to be not canonical. So it's not part of the chain that people should follow, even if it's like you have all of these committee votes. And this provides an important safety guarantee. So basically, if you wait for a shard block to be confirmed, then you do something on chain based on the knowledge that the shard block is confirmed, like you do some operation in a rollup, you publish some kind of fraud proof or whatever, then if it turns out that the shard that committee was bad and the shard block actually is not available, sorry, I should say available instead of confirmed. If it turns out that the shard block is not available, then well, the chain will get reverted, and so whatever you did based on the assumption that the shard block is available will also get reverted, right? So you have this kind of atomicity guarantee. Now, the next natural question is, well, okay, so we have this rule that says that if the beacon chain confirms, so not just includes, but also confirms, which means it also includes enough votes for a shard block that's unavailable, then theoretically you're not supposed to follow that beacon block. But what's the point of that rule when nodes are not supposed to be actually downloading all of these shard blocks personally? And this is where data availability sampling is going to come in. But first, just a bit of a kind of motivation for why we need data availability sampling, so why we can't use just a committee. So the first kind of concern is, well, what if 1/3 of some committee is corrupted, right? So basically, there's always the possibility that an attacker actually does kind of gain access to a fairly large portion of all of the staking participants. And we want to have second layers of defense to kind of take care of this possibility. And because if we don't, then there are some nasty things that can happen, right? Like basically the problem is that, or one of the problems is that even though you theoretically need 1/3 of all validators to be willing to participate to push an unavailable proposal through, it only requires the actual committee, the 128 validators, to actually sign off, right? To actually publish the signature that says, like, yes, we think this proposal is available when actually it's not. And so there isn't really a way to kind of, even with a hard fork, even socially, like just no way at all to significantly penalize the attacker. And then the second kind of nuance is, well, what happens if 1/3 is offline, right? So in general, like in Eth2, we have this goal of trying to thread the needle between being both kind of having both asynchronous safety and, as much as possible, and liveness, even if large portions of the network are offline as much as possible. Right. So this is why, like for example, we have the fork choice rule, and not just relying on the 2/3 finalization. And so it would be a shame if we kind of lost that ability to be able to get some things done, even if more than 1/3 are offline for these shard blocks, right? So basically, if we just have a 2/3 threshold, then if more than 1/3 are offline, nothing gets committed. But then there's this other option, which basically says you have no fixed threshold, and either you have a dynamic threshold that adjusts based on what portion is online, or you just need more votes from a committee in favor of a block than against it. And the problem is, if you take either of these trade-offs, then an attacker could potentially kind of find some way to knock many nodes offline, and they could basically reduce this threshold from 1/3 to, or the amount they need to attack from 1/3 to something even smaller. Like if they knock half of the nodes offline, then it goes down to a 1/6. Now we do choose option 2, right? So we choose the trade-off of being more vulnerable to attackers instead of being more vulnerable to just long periods of the chain completely halting, or at least the chain's ability to confirm shard blocks completely halting. And
hey Vitalik, before data availability sampling, do you maybe see if there's any questions about the committee mechanism? Because these two are kind of like additive, and one, the data availability enhances the base of the committee.
Yes. Okay.
Yeah, I have a question. So for option 2, should we still respect the honesty minority model or not?
What do we mean by respecting the honest minority model?
Do we still, I think the last time I checked is that we need some like 14 nodes to be online. So I guess for option 2, let's say there's like only 13, then what do we do?
Oh, I see it. Right. So if even the honest minority assumption, which is like that there's a total of like some small number of nodes, so some small number of clients, so not even validators, just clients, I'm checking every shard. Like if that assumption is broken, then basically we're screwed. Like there does come some point at which we are screwed. But like, as long as there are clients on the network, then like my opinion is that the chance that we have an actual like honest, that we have so few clients checking the shards that even the honest minority assumption is not satisfied is very small.
Any other questions on committees?
I have one. I think it's about fork choice. So assuming we have a beacon node that has no validators, it's just sitting there listening, how does the fork choice know that the block is available, please?
Great. So this is what I'm about to talk about. Right. So data availability sampling. So basically, this is this kind of second layer of defense to prevent unavailable blocks. Right. So the idea is that we don't want to just rely on committees. We want nodes to be able to personally get at least like some medium level of guarantee about whether or not a shard block is actually available. And we want nodes to be able to make this check for every shard, every slot. Now, there's a trivial way of doing this, which is to download everything. But if they download everything, that basically means that every one of these nodes would have to download 1.5 megabytes a second. And over time, we expect the specs on the chain to increase. So it might go up to like over 10 megabytes a second. And then you have to multiply that by peer-to-peer overhead. And so it just becomes unrealistic for all but the most powerful nodes. So here we have this clever mechanism where instead of the nodes downloading all of the data, they basically, each client randomly chooses some set of positions and they try to download only the chunks at those positions. Right? And the client accepts only when they download the chunks at all of the positions that they asked for successfully. So Dankrad went over this briefly, but the basic idea is that if, let's say, you make 20 samples, then in the case where less than 50% of the data was available, then with probability of like 1 minus 1 over a million, at least one of your sample checks is going to end up failing. And so if all of the checks do succeed, then you know that with a probability of at least 1 minus 1 over a million, at least 50% of the data actually is available. And if at least 50% of the data actually is available, then you can use that to recover the entire data. And so like that's just because of how the erasure coding works. And so random sampling actually does prove availability of the block. So the key guarantees that sampling provides. So this is the kind of honest minority assumption, right? So if there's D is the number of positions that you need to recover the full block. So now I mentioned before, right, that a block is going to be up to 500 kilobytes, or more specifically up to 16,384 points. But we are doing kind of 8 points per sample, and this is just an efficiency optimization. So we actually have 2,048 samples. And then K samples per validator looks like that's about 20. So if you have about 100 honest, and then right times 2. So if you have at least kind of 200 honest clients accept, then with high probability the block is available. All other honest clients will accept. So you have the same kind of convergence guarantee that you have with just regular full block downloading. And now, if the attacker can theoretically fool a few clients, right? The way that they fool a few clients is if the attacker publishes none of the body, and then they just wait for clients to kind of have requests, and they only satisfy those requests. But the attacker would only be able to fool a small percentage of them, and only with a very small probability before they would basically need to publish enough data that when the clients rebroadcasted, there would be enough data to just recover the entire block, by which point they'll have published the block.
And if you're in a state of being fooled as a client, what are you using to decide that it's not just not available and I should keep working? Is it like a heuristic? So I keep seeing attestations come in. You know, what are your thoughts there? Right.
Oh, I see it. So one important nuance here, right, is that there's no time limit on DAO sampling. So it's similar to it's not the sort of protocol where like you run this procedure and then you wait 30 seconds. And if nothing comes back after 30 seconds, you decide the block is not there and that's your decision. It's more like you accept the shard block as available only once you get back all of the queries that you made at the beginning. Right? So if you make a bunch of queries and you only get 19 of them after, say, 10 seconds, then you just wait. And then if the 20th comes after 2 minutes, well, that's fine. Then the shard block was only available to you after 2 minutes. So and this is kind of similar to how just downloading a block works, right? Like you accept in a non-sharded blockchain, you accept a block as available only once you've downloaded. And there's no, if you receive a block, there's no time limit for when you, after which you decide that the parent is unavailable and you throw it away forever. It's just like you just keep the block around, and then whenever you receive the parent, then you accept the parent, and then you would accept that block as well.
Thanks.
Okay.
What is the expectation, and for how long will it be available?
So the blocks should be available like as a long time, I think would be the answer. But to give some more concrete answers, so the blocks would get rebroadcasted through some subnets, and I'll talk about the subnet structure later. And then the nodes are going to kind of bounce between different subnets, and so like the mechanism for just kind of grabbing the data from the subnet might work for potentially a few minutes, but then we would also have some longer term DHT structure, and the clients can obviously also try to kind of poke in and make requests to the DHT, and blocks could be available in the DHT theoretically like months or years, or like however, like the only constraint is basically nodes storage capabilities. Like if everyone had super big hard drives, we could make it be forever.
One thing to note is in the committee construction, there's a proof of custody construction which has a tunable parameter for how long they're expected to keep it or make a crypto economic commitment that they have it or can find it. And so that number kind of provides at least the baseline amount you'd expect this network to be able to serve before it maybe goes into secondary sources outside of the immediate network.
What would be the minimal time then?
That parameter in the spec is like 80 days right now, but depending on the storage requirements that we'd want to have on consensus nodes and per validator, that could be tuned.
Okay, and to produce a beacon chain block, how long is the shard block needed?
I mean, theoretically, the entire kind of cycle of producing to attesting to confirming under optimal conditions could be finished in a single slot.
One thing I'm worried about with data availability sampling is right now we have lots of disk traffic, and we also want to use pruning. But if we need to keep the block open for 18 days and we only have a slot to reply, that means that pruning is difficult.
So I guess one thing to be clear about, one thing is that this is only for validators, and it's not for non-validating clients and don't really have any responsibility to keep data. Another thing I meant to mention is that there's no requirements to respond to someone else's message within a single slot, right? You do get rewarded for including and kind of attesting to and processing a shard block within a single slot, but that's we do things within a single slot already. That's just the progress of the beacon chain. But ultimately, if you are a validator, then yes, you would have a responsibility to store basically whatever number of epochs are in 80 days times on average 256 kilobytes of data.
Proto, you have the numbers on that, don't you? Do you remember what it was, the total storage requirement per validator on an 80-day window?
Hold on. 1 EEC is 22048 epochs, and then 80 days, I think it's 72 days, so it's 8 EECs, so that's 16,384, and then multiply by a quarter meg, that's 4 gigabytes.
Right. And so from a consensus perspective, that's all per validator kind of requirement, which scales linearly, at least for a while. And pruning from a consensus perspective could also happen after that window.
And
so
another thing is that it is perfectly okay to have the shard block data be on a hard drive or even HDD or like whatever kind of relatively high latency medium.
Right.
Like basically, if you're sampling for one of these, like if you're sampling in real time, then we want to try to optimize the real time sampling and make it fast. But if you're sampling after the fact through the DHT, then like, you know, if it takes a minute to respond, that's not that bad, because you're hours or days late anyway.
Right, and you're gonna go over that optimization, how to do live sampling, right?
Yes.
Cool.
That's 2 slides from now. But just one quick slide is this. This is just briefly going over polynomials again. So basically, the way that you do this recovery thing is that in the header you have a polynomial commitment. So this is and the polynomial commitment is a commitment to a degree d less than 16384 polynomial. But what we do is we generate evaluations and proofs for evaluations at more than d points. So it's 2 times the max degree points, 32768. And any d plus 1 of these points can be used to recover the entire polynomial. And the special case of this you probably learned in high school is that like the d equals 1 case, a degree 1 polynomial, a line, any 2 points on a line can be used to recover the line. And then for high degree d greater than 1 polynomials, d plus 1 points can recover it. And so that right. And also, as I mentioned before, there's also a proof that proves kind of a bound on what the degree is. And you can think of that proof. It's actually also like just one more. I think it's one more G1 point. So it's just another 48 bytes. And what else did I want to say about this? Right, and just like the number of kind of what the size of a block is, it just is also part of the header. And so, like basically, if a block is full size, you need 50% of it to recover the whole thing. If a block is like quarter size, you only need 1/8 of it to recover the whole thing. So sharding by subnet. So this is where we get to how this is all supposed to look from a peer-to-peer point of view. So we have 2 kinds of subnets. I call them horizontal subnets and vertical subnets. And so it's good to think of them as being a grid. This diagram is a little bit wrong. Like actually, ideally, we wouldn't just have 64 horizontal subnets. Ideally, we would have 2048 horizontal subnets. So one for every kind of pair of a slot in epoch. So like whether it's the 0th slot, 1st slot, 2nd slot, all the way up to 31st slot in an epoch, and the shard from 0 to 63. And the horizontal subnets to just like store and broadcast the full body of the shard blocks corresponding to that slot shard pair. And then you have vertical subnets, and vertical subnets store the ith chunk of every shard block. So the 3rd vertical subnet just stores chunk 3 of every shard block. And vertical subnets are how we make data availability sampling concretely kind of simple for validators. Basically, what happens is that a validator chooses a set of indices, and then they just join the vertical subnets that correspond to those indices. So and basically when they're on those vertical subnets, they would just receive the ith chunk for just every shard block that there is. And so they'll be able to just like, well, basically they're able to do the data availability sampling completely passively.
Right, and they're listening to that global subnet that has the shard block headers, so that they have the basic information to verify those against.
Yes, right. And the shard block headers, yes, they get published in the global subnet, and they also get included in beacon blocks very quickly.
How is the vertical subnet shuffled, or is it shuffled at all today?
My preference is to just not bother with shuffling. I don't really see much reason to do it, but if we want to, we can.
I guess one reason is because block could be different size, right?
Well, right, but like it's not the case, like, but the subnets don't have different load, right? Like, I see. So the polynomials have different degree, but every block has the same number of samples, right? So basically, like, if let's say we imagine hypothetically that there's a block that has like only 2 points in it, so the block itself has like 64 bytes, then that would be a degree 1 polynomial. And so like if just in reality, it's a bit more complicated, but basically you would have, like, if the coordinates were just sequential, then over here, like, you would have the number 3, here you'd have the number 5, here you'd have the number 7, here you'd have the number 9, here you'd have the 11, and number 11, and so forth, right? So every one of these squares does get filled. It's just that when a block is smaller, it has a higher degree of redundancy.
Got it, thanks.
A quick question from previous slides. It seems like with polynomial commitment, Merkle roots are disappearing. Are we removing them?
There are no Merkle roots to shard block data. There are the Merkle roots that are already part of the protocol are still staying for now.
So SSE still exists and the Merkleization there happens, but then at a certain point, as you dig down into the shard blocks, you have a polynomial commitment instead of extending into the tree.
Mm-hmm. So one longer term thing we may want to do is just like doing a more thorough replacement of polynomial commitments with replacement of Merkle trees with Cat-A commitments. I don't know. There's been some research on Merkle trees that Dankrad has been working on, and also there's been a lot of work. Or I've also suggested that Cat-A commitments can be used in Eth1+X for code Merkleization. And the reason why I think they're really good in that use case is because in code Merkleization, the witness for the code needed to process a particular transaction just tends to kind of randomly jump all over the place, right? Because contracts aren't really designed to optimize for kind of execution being contiguous. And with code Merkleization, you just need, because all of the code is separate for every chunk of code you access, you need a kind of separate branch going to it. So there's a lot of data overhead. But for Cat-A commitments, you don't really care about that, and you just need a single 48-byte proof for any arbitrary subset of the code, regardless of where those chunks are located. So like basically, there's reasons to move toward like using Cat-A commitments more and more in other contexts as well. Okay, so broadcasting procedure. There's, I think, there's 3 broadcasting games that we need to, I think, worry about. I forgot to mention the third one here. So one of them is the initial broadcast game. So when a proposer publishes a shard block, they generate the shard block, including all of the proofs. Then they push the entire shard block to the corresponding horizontal subnet, and then they basically push the chunk I to the ith vertical subnet. You know, this third step is a bit more involved because we don't want the proposer to have to be on every vertical subnet. Instead, what happens is basically the proposer just publishes to the horizontal subnet. The attesters pick it up on the horizontal subnet. The attesters then, that's already about 100 of them. And then the attesters themselves have a lot of peers. And then they ask like which vertical subnets their peers are on. And so between all of the attesters and all of the peers of the attesters, there's just like a lot of nodes, and they are able to kind of collectively cover rebroadcasting each chunk to the corresponding vertical subnet. Now, recovery. So recovery is important. This is kind of case where you have a malicious proposer where they, let's say, they don't publish to the horizontal subnet, Instead, they just publish some chunks to the vertical subnets, and maybe they only publish chunks to some of the vertical subnets. So they publish enough data to get most of the clients to accept the block, and they publish enough data to recover the block, but we actually need to do the recovering. And so here what happens is, it's like, first we run step 3 here in reverse order. So we try to kind of pull, like, the nodes in the committee in the horizontal subnet tries to pull the chunk I from the I's vertical subnet. In some cases they might succeed, in some cases they might fail, but like altogether they would succeed. And then they would just rebroadcast those chunks in the horizontal subnet. Then in the horizontal subnet, there would be enough chunks to recover the rest of the blob. And then just anyone just like recovers the entire data, generates all the proofs, and then they just rebroadcast the same way they were if they were a proposer. And then the third game is basically, well, for longer term access, we have this DHT, and the data needs to be published onto the DHT, and clients needs to be able to kind of grab like specific shard headers or specific indices from the DHT.
On the recovery, that's primarily, this is a failure mode, right? Like RA,
Correct.
It didn't quite fail, but it almost failed, and now I need to recover, and usually wouldn't have to happen?
Yes, correct. So the recovery is only required when there is either a dishonest proposer, or it might occasionally be required if there's like some network hiccup, and let's say the chunks get broadcasted onto every vertical subnet except for one, and then the attesters that are the clients that are looking for that one last sample are going to be kind of spinning their wheels, and they have to actually kind of get that data back, and so you would need to regenerate it.
Mm-hmm. And even practically in that standpoint, if I'm on a horizontal subnet and I'm listening to one of the I subnets and I don't see it, I can just send that proof instead of having to go recover because I saw the full thing.
Right, this is true.
So it's like, it's the backup of the backup probably in many cases.
Right. Yeah, this is true. If the proposer is honest, then the thing on the horizontal subnet does exist, and so right.
Are there some thoughts about how we might coordinate recovery so that everyone doesn't do it at once?
I think also a good question. So I think this is one of those kind of step-by-step things. So the pulling from vertical subnets thing is, I think, just a collaborative effort that everyone should participate in the case where the data on the horizontal subnet is missing. And then as far as like who does the recovering and the rebroadcasting, it's definitely a good idea to kind of nominate a limited set of actors. And if we want, we could just like reuse the mechanism that we use for attestation aggregation here. But I don't know, we think about it.
Right. And I do want to mention on that third item, chuck it into a DHT. There's a lot of thoughts, I think primarily led by Proto and a little bit of in conversation with Felix on how you actually do go and find or share the fact that you have more historic block data rather than this live stuff called in the last few epochs. There's many things in its design space, but I wouldn't say we have 100% the design that we want to use here. So definitely some open questions and some like trade-offs in this space still to explore. So if you're interested in that problem, that's something to dig into as well.
No. Okay. So I guess any questions on sampling before this was the last slide.
So practically it looks like I'm in a horizontal subnet, and I'm listening to shard blocks sometimes as a validator. I get assigned to one here or there. And then all the time I'm listening to a subset of the vertical subnets and checking those against all the shard block headers that I saw come in. If I see what I think is unavailable data get confirmed into the beacon chain by a committee, then I actually use my fork choice to not follow that beacon chain because I think it's unavailable. If at some point I actually see that data is available, I bring that back into my fork choice. This would allow, if the majority of validators are honest in doing this, they're not going to finalize something that's unavailable.
Mm-hmm.
Okay.
I have a short question.
Okay, so my question is very simple. Won't it be easier for the next shard block proposer just to include a blob of data rather than falling back to the recovery mode?
I mean, no one has like a choice between proposing and recovering, right? Like if you're the proposer, then you should propose. Oh, right. One other thing I forgot to mention is that like there's no linking between one shard block and the previous shard block of from the same shard, at least right now, right? So there's and even if there was a linking, that would only be to the header. So like it's not like so like basically the jobs of the different proposers are kind of independent of each other, right? So and in general, like the people who would be doing the recovering and the people who would be doing the proposing are different.
So it means that the same blob is not possible to be included like in the one block and included then next to the another one.
Correct, because the header already contains like what the slot in the shard is, so the header can only be included in one position. Right. Now, obviously, you can have multiple headers in multiple positions that just happen to have the exact same content, and that's fine. Like content, I mean,
like
body.
the payload, yeah.
Yeah. Okay.
I did have one question. Sorry, it was about the fork choice one. Perhaps it was poorly worded, but so in fork choice there's the tight coupling. If say a non-validating node is just following the beacon chain, does it make does it need to like actually query for data availability, or does it just make like assumptions based on the pending shard bit fields?
In my opinion, nodes should do data availability sampling if they have the capacity for it.
Wouldn't that make it kind of like ON again? Like you need to be washing all of the shards?
No, because for sampling, you only need to be processing a O of 1 data per shard.
Right.
Okay, you still have to.
So like basically,
cover
like
all the shards for just a little bit.
Right. So like the total amount of data in the system is O of n squared. The beacon chain is already O of n, and data availability sampling on all shards is also O of n.
So you can follow all shards all the time and know that the data is available. You could do data availability sampling, or you can follow some shards and then do data availability sampling for the rest of the shards, and still know that the data with extremely high probabilistic guarantees is available. You could then not follow any full shards, do data availability sampling on everything, and get those same guarantees. You can certainly not just follow the beacon chain pretty lightly, even as a light client, and kind of rely on attestations and finality as your signal. And maybe you could do data availability sampling on a subset, although the way that the vertical subnets are constructed, you would generally just be seeing the points for everything on that indice. So, I mean, it is certainly a design. You can design certain types of nodes that don't do sampling, but it's definitely a good thing when users are doing sampling.
Yeah, and the one class of node that would not do sampling because it's relying on its majorities anyway is the light clients that are using sync committees.
Right. And I guess
so. I mean, even though it's like in the long run, I think it will be possible to have a node that does that and does sampling.
Got it. Thanks. And I had just one more regarding publishing publishing the shard block header and then a bunch of proofs about it. I'm just concerned about publishing lots of related messages all at once might make it might jeopardize validator privacy.
Okay, so validators, let's see, they publish, right, so a validator would publish the shard block, which is the header and the body, and that's just like similar, like that's not really different from how beacon block publishing works. Then you have the broadcasting game, and the broadcasting game, the one, right, okay, so the one piece of like significant information that the broadcasting game might reveal is like which vertical subnet you're currently in, which reveals like which the more you can know about which vertical subnet someone's in, the more you can potentially kind of target and try to attack them. And so, okay, so you do need like, and for that reason, we do have validators like shuffling which vertical subnets they're on. And I think the current approach is to like switch out one of those every slot.
Right, so there's the kind of random shuffling here. I think it is a valid point that when you add more duties and add more consensus messages and more things that people are listening to, you're certainly leaking more information. And things like secret leader election and other like nice to have they might end up critical, but nice to have from our perspective right now. Upgrades are really valuable there.
Agreed.
Yeah. I just think, I think there's something about publishing multiple related messages that makes it more obvious, because you can start to reason about, like, if you got lots of these messages from the same person, they're probably closer to the source of it.
You know, there may be ways to try to like anonymize the rebroadcasting games more.
Right. Well, one thing and I don't know if this makes privacy better or worse, but if you're not operating on the assumption that the shard proposer is necessarily on all the vertical subnets, and so there is like a rebroadcasting that's likely to happen from those others that are in the shard committee to their own I subnets, which might help obfuscate or might actually help leak information. I need to think about it more. That's your assumption, Vitalik, right? Is that the shard proposer isn't necessarily hitting all those I subnets or every single subnet?
Correct. This entire proposal is designed around everyone needing, each validator only needing to be on O of one subnet.
Right.
Okay, so last slide. This is just a kind of an aside on how applications would actually benefit from this data. So basically, in the beacon chain state, we just have a Merkle tree of the confirmed commitments. So just a tree where you can look up like what the confirmed commitment is at a particular slot at a particular shard if there is one. And the way that a rollup currently works, right, is that like rollups basically you kind of work over, like you refer to blobs or batches of data by their hash, but you do have to actually prove that the blob is available. And so when you submit a batch, you provide the call data, and then like as part of the transaction, then within the transaction, you hash the call data, and then you just like save the hash root of the call data in the list of data roots in your storage. And then when you make a fraud proof, the data root gets saved. And then you just, once again, you hash the portion of the call data that's providing the blob or the batch data, and you just check that it equals the data root. So that's how rollups work today. A rollup using Eth2 data, basically the call data will to publish a batch, the call data will not go in the transaction contents because, well, there's only O of n space for a transaction contents, but there's O of n squared space in the shards. And so you would want to just use the shard data directly. And so basically you would just kind of poke into, like you would use some method to get recent confirmed data root that would accept a slot and the shard as an argument. And after the merge, the beacon chain state could be accessed from the Ethereum execution in exactly the same way as the Eth1 state can be. So you just get the recent confirmed data root from the just by looking at the state. And then in a fraud proof, you actually would take the data and you would include it in your transaction, and then you would just like make the cat commitment kind of inside the EVM, and you would verify that the cat commitment you generated actually is the same as the commitment that got saved.
Right. One thing to note, definitely if you're a rollup provider listening to this, the use of Kate commitments is going to change how you do things in rollups. On an optimistic side, optimistic rollups, not terribly much. I think the commitments need to change and some of the proving there, but a lot of the core mechanics can stay the same. Whereas in the ZK land, it's a different cryptographic construction, and so there's probably some like more fundamental things to rework and stuff. So as this becomes more reality, keep your eye on it. Any other questions for Vitalik?
With the ratio codes, you can also produce arbitrary number of encoded blocks or samples. Right now, you are proposing to do 100% of the real sample data, which means that every byte of data that is produced in the network is double with this proposal. Is this already completely 100% fixed, or is it possible to explore other sampling techniques with the ratio code, like just 80% or 20%, or because there is this trade-off between data availability and storage, of course.
Right. It's definitely possible to explore other points on the trade-off space. Though one thing to keep in mind is that if we try to make the bounds tighter, then the number of data availability samples that you need to get the same security guarantee increases quickly. So, like for example, if 50% full block requires 20 samples, then a 70% block will or full block will require, or a block where the data needed to recover is 70% of the entire block would require 40 samples, and then a block where the data needed to recover is 84% of the blocks of the entire data would require 80 samples. So basically the inefficiency on that side would shoot up quickly. Well, actually, to be clear, this proposal says 50% is for maximally full blocks and then 25% for average full blocks.
What determines what goes into shard?
Can you repeat that?
What determines what goes into which shard?
The shard proposers do. Each shard proposer decides what data to put in to the blocks that they can create.
The mechanics below that would be some sort of data fee market and likely some sort of data transaction format, and likely a data mempool, transaction mempool related to shards that potential proposers for that shard are listening to and know that it's valuable to include such data into their blocks. And I mentioned in the chat, I'll see if I can find the links. There's a couple of different shard data fee market proposals from the past 6-7 months on ETH research that go into maybe the mechanics on how fees can be paid here.
If later we were to add execution in shards with this approach, how difficult or like easy would that be?
Basically, we would have to just extend the shard header structure to add a state root, and then we would need to decide what mechanism what kind of backup mechanism we would want to use to make sure state roots are correct. Like, would we either have a fraud-proof scheme that could revert the state roots if it turns out that someone computed them incorrectly? Would it be, or would the state roots just be ZK proven?
There's no independent chaining of these shard chains, and so these shard blocks, so they have to be kind of like confirmed independently. But with execution, you kind of want more of a strong notion of like chainedness and a chain being able to be built without necessarily being confirmed in the beacon chain every slot. And there's actually a reasonable amount of consensus complexity that appears there. And my intuition would be, if we build shard data, and it is a valuable resource to the ecosystem, to keep them as shards that are just for data, and then like maybe have additional execution shards, so you have kind of like two different zones of things that are happening in consensus. And that's there's a lot of different design trade-offs there though. Okay, we're at our 2-hour mark. Any last questions for Vitalik? Thank you.
Yay.
Appreciate it, Vitalik.
Thank you.
So next up on the agenda is we're shifting from, like I said, we have the beacon chain. The beacon chain is a bootstrapped proof-of-stake consensus, and there are two major things that we want to do with it. One is to come to consensus on Eth1, on Ethereum. And the other is to facilitate more scale in the Ethereum ecosystem through sharding, which was previously discussed. I'm listed as a speaker. I'm just going to give the intro. Mikhail and Guillaume and a number of others in a small working group have spent, I don't know, the past 8, maybe more months, kind of digging into the design landscape of what an Eth1, Eth2 merge looks like. And there are something that are beginning to look like specs, and there are prototyped merge testnets and some other fun stuff. There's a lot of things to think about. There's a lot of like design trade-offs here. There's a lot of things to think about, like what actually happens at the point of the merge, what are the security considerations there, other things like what has to change for users and what can be largely stable. And from our understanding, a lot of it can be largely stable, a lot of the same APIs, same endpoints, that kind of stuff. To set the stage, I just wanted to talk about how I see Eth1, how I see Eth2, and what's kind of been happening in the different zones over the past couple of years. Essentially, the work that's gone into what we call Eth2, which I think is a terrible name, was to build and bootstrap a proof-of-stake consensus mechanism, a consensus engine, to supplant Ethereum's existing proof-of-work consensus engine, which if you've worked on an Eth1 client, likely you got that proof-of-work component stable and haven't really done much with it since, because it's small, isolated, and it drives things, but you don't have to think about it much. What I see, the merge of Eth1 into Eth2, of this like proof of stake beacon chain that was built and facilitated in what we call an Eth2 client. And if you've read anything that I've written recently or seen some of the posts we've put out, the unification, this is kind of like a beautiful unification of layers. Eth2 clients are very sophisticated engineering teams that can build out proof-of-stake consensus mechanisms, and Eth1 clients do incredible work in the user layer, in state and execution, transaction management, and everything kind of user land. And so what Mikhail and Guillaume have worked on is kind of the marriage of these two, defining a communication protocol between an Eth2 client, kind of the driver of consensus, and an Eth1 engine, which is a modified Geth, which says, okay, I'm not listening to proof of work anymore, or I'm not listening to Clique. Instead, I'm listening to this locally defined RPC that tells me, there's a new block. Hey, I'm thinking about producing a new block. Can you give me a bundle of transactions, that kind of stuff. So really, I think this is pretty exciting in that we have people that are very sophisticated in this one layer of proof-of-stake consensus and people that are very sophisticated in this other layer, kind of like user land execution. And I think that through this merge, we get to leverage the sophistication of software on both ends of the stack. And I'm very excited about it. And on that, I will give it to Mikhail, who's going to talk about things from the Eth2, kind of like Eth2 driver consensus side. And then we'll pass it on to Guillaume, who's going to talk about Catalyst, which is a modification of Geth to be this Eth1 engine that lives adjunct with an Eth2 client. So I'll turn it over to you. Thanks, guys.
Thanks, Danny, for this nice introduction. Can you see my screen? Can you see the presentation?
Yep.
Cool. So let's get started. So in a very simple understanding and a very simple wording, and according to the most recent proposal, the merge is a tight coupling of the beacon chain with the Ethereum mainnet. So what's affected on Eth2 side is like, in terms of the spec, all the parts of the spec are affected. I will just go through the change step by step. We'll stop at each slide for questions, but feel free to stop me at any point in time to ask the question if you need to. So are there any questions that far? Okay, let's move on. So the first part of tight coupling is that the beacon block body gets a new field, which is called executable data, which is probably not the perfect name. Yeah, any inputs on like the new name are very welcome. So let me just turn off my earphone.
Can you hear me now?
Yep.
Great. Sorry for that. Okay, so the executable data, if we take a closer look into it, it's just several fields, almost all fields of basically Eth1 block. Executable data doesn't include the fields that are related to the Eth1 consensus. It also doesn't include an extra data field. We also can see some leftovers like difficulty here. It's going to be removed. Don't pay much attention to it. Also, there are parent hash and the block hash. They are Eth1 styled block hashes. And we also can get rid of them, of these two, but it's a bit of an exercise because you need to somehow identify the block, the Eth1 block that you're building on and that you're inserting upon. And at some edge case, at some cases, it introduces the circular dependency if we, for example, try to use the beacon block root. So it's a bit of an exercise, but it's doable. So the transaction structure is just a copy of what we have in the Eth1 currently. So the other affected structures is like the beacon state, but it's not much of affected. And since we use like the more advanced deposit processing flow after the merge, we're able to deprecate the ETH1 data pool, which is nice. So we don't need ETH1 data votes anymore. But we will still use the ETH1 data, which is like considering to be removed at some point in the future. We'll talk about deposit processing later on, a couple of slides later. In terms of size, currently the Eth1 block is like 40 kilobytes on average. This is according to the current gas limit, which is on Ethereum mainnet. And for the record, the beacon block is like 100 kilobytes or even more in average. So it's not like a big gain in terms of size for the beacon block. It's like 30%, something like that. So that's pretty much it regarding the structures. Does anyone want to ask anything here?
So something I meant to mention at the beginning is this particular proposal right now, which has the ETH1 integrated essentially as a payload in ETH2's consensus, ends up looking like early proof of stake designs, like the Casper FFG proposal and things, where essentially you're taking ETH1 and you're adding a bunch of proof of stake consensus messages, to facilitate them living kind of in the same chain. And this, instead of attaching it onto ETH1, was bootstrap that consensus independently and then slot ETH1 such that in the payload, the consensus payloads and the execution and user layer payloads live in the same place. So if you're familiar with previous designs, this is kind of a roundabout way to get to where we were going a couple of years ago.
Okay.
And one question I would have would be like, take the gas price, for example. How does that relate to the balance in Eth2? Or say the, the deposits or whichever piece of balance like data you take?
It's not related to the balances on Eth2. So gas prices and Eth1 balances stays within the Eth1 part of the merged chain. So Eth2 balances are heavily used by the system, by the consensus layer. And they will be like, there will be withdrawals and deposits in the same fashion we are discussing them as of today.
And as Mikhail is going to get into, a lot of these, like, essentially you have all of the ETH2 consensus validations, but then you also have like a call to ETH1 validations, which are going to validate this transaction list, validate the gas use, the gas limit, that kind of stuff, in a very similar context to what's validated on ETH1 today.
I have a question. So what is the Coinbase used for in this setting?
So likely the actual block reward within like ETH1 execution would be 0, but if the Coinbase, which I believe is used to collect transaction fees from transactions, that would go in there. So if I'm a beacon block proposer and I propose this transaction list for ETH1 execution, I'm also going to specify where I want my transaction fees to go to in that Coinbase.
Yeah.
Yep, and this Coinbase opens like a path to the Eth1 engine market. Like if you can expose your like Eth1 engine instance to produce a block for one's validator who don't want to run the heavy Eth1 node. This is one of the options here.
To confirm, so we'll now have two sets of validations, like the ETH2 validations and the 1x validation and the ETH1 validations. And that second set will happen through a bunch of RPC calls, so like it'll call into an ETH1 client.
Yeah. I'll talk about it, just like starting from the next slide. So
Cool.
Practically, that ends up being a design detail because you could write an aggregate client, but we do have these like largely clients that are separated in terms of concern. So practically, yes, the RPC would facilitate that validation.
Yep. Okay, so let's go to the next one. So the validator. The validator will have to obtain yet another portion of the executable data. How does it do it? It was mentioned that the JSON RPC is used. So the validator just prepares some parameters and makes a call to Eth1 engine, asks it to create another portion of executable data. Eth1 engine goes to the transaction pools, gets all the transactions that it finds reasonable to include in this portion of data, runs them, assembles a block, and returns it to the validator. So a couple of things about the parameters. First of all, we want to use the most recent rundown mix for the sake of better randomness. So we pre-compute it here with the recent rundown reveal that will be included in the same beacon block. And we expose beacon block roots to the EVM. And we also expose this slot to the EVM to make it possible for the to access the beacon state outside of the EVM. So we get this passed to the Eth1 engine, and it exposes it in the same fashion as block hashes are exposed to date.
Right. So a lot of that ends up are nice to haves and exposing extra information to users about like the ETH2 consensus. Like for example, you don't have to put the Randall mix in there, but if you expose it to transactions via an opcode, it's a nice potential source of randomness. Something to also note is this ends up looking a lot like, I think there's a get work RPC call on ETH1 clients today, which essentially doing the work of like assembling a block for mining. And this is similarly like assembling a block for the proof of stake proposer.
What are the latency requirements here? I mean, if a validator is calling ETH1 and then waiting for a response before it produces a block, what's the timing structure like?
Yeah, it's a synchronous call, obviously. And I guess that requirements that with regard to latency, that we can gain them from the timeline of the slot. So we need to. I'll speak about it later on. But what we need is for the network to be able to produce, propagate, and process the block like it is now. But with including all these latencies can be included like in the processing, in the proposal time. I don't think if they are located like in the same data center, it should not be like big latency. If these two parts of the client are located on the same machine, it's like just few milliseconds, I guess. I mean the latency in transmitting the data. Of course, producing a block takes all the time that the execution of transactions of the block takes.
Yeah, because I'm thinking about it from the point of view that right now ETH1 kind of just feeds into ETH2. It's a one-way street. But here we create round trip, right?
Yeah, we can implement it like. I mean, we can like have this server-side push or whatever it's called to push the block whenever it's ready. If you're meaning that.
Assuming get work works today, the latency here I don't think is incredibly high. I think if you're located on the same machine, which is generally what we're designing for, that it's probably not much of a concern. I think if you're actually dealing with remote machines and round trip communications, yeah, you might run into an issue on block production times.
Well, the curiosity here is that we provide the ETH2 data to ETH1 at the same time as we ask ETH1 to produce the executable data. And I'm curious why these two necessarily have to, or do they necessarily have to be linked to each other like this synchronously, or could you think of them as two separate feeds?
So if you're going to have ETH1 transactions and things as the payload in ETH2, then you have to have them tightly coupled. But in terms of what some of these variables are doing, are providing essentially read access in ETH1 to some of these consensus layer items like the Randall mix, recent beacon block roots, and that kind of stuff. Thus, you do need that kind of two-way street. But you could also have ETH1 that never learned about the beacon chain and couldn't really communicate with it in such a way or read from it. And you wouldn't have to necessarily provide those, but then you're limiting a lot of functionality, and likely some of this ends up being necessary for handling deposits and withdrawals.
Transition. We add the process executable data function to the end of the process block routine. What it does, it actually prepares like the same, almost the same parameters as the validator does, and sends these parameters alongside with the executable data batch to the Eth1 engine, and the Eth1 engine inserts this block into its one chain it's producing, and returns the flag of whether the execution is succeeded or not. Yeah, then the Eth2 side verifies, validates that the execution is succeeded. Otherwise, if it's not, then the beacon block is considered invalid. That's like yet another call to the Eth1 engine. Looks pretty similar, pretty tiny. So it's also a synchronous call. In terms of a slot, so we need to process a beacon block and we need to process Eth1 block within the same slot. And some like option for optimization we'll talk a bit later. So that's it. That doesn't look like a rocket science. Cool. Okay, regarding deposits, what's on the left? You can see like the ideal deposit processing flow, which is the proposer of a slot takes the deposits made in the previous, in the previous slot, takes the new deposits, builds like the proof that is linked to the previous beacon block root, and include this batch into the beacon block that it is predominant. So why do we not go in straight to this flow? Is because of the Eth1 state root is the Merkle-Patricia tree root, and there is a plan to change it to the binary tree, or even replace it with the polynomial commitment. So this is why we, for the moment, we reuse pretty much the same logic of deposit processing, but one major change. We use the Eth1 data produced by the previous Eth1 block because of the tight coupling Eth1 execution to the beacon chain. We can do this, and we process deposits in the same fashion. But in order to make sure that Eth1 data that published in the previous block are valid, we add this check for Eth1 data correctness into the fork choice on block routine. This is possible to do because when we tight couple the execution to the beacon chain, the Eth1 data produced by the previous block becomes deterministic, so we can exactly verify them and say whether they are valid or not. So that's how it's proposed to do in the current version of the spec, like the schema on the right. And the state transition function updates the Eth1 data in the state, in the beacon state, like per each slot. And it allows for like inducting deposits made in the previous slot, right in the next one, which is great. So, anything to ask here? Okay, cool. So a little bit of speculative slide. This is like an attempt to reason about how Eth1 block processing time, how Eth1 block processing impacts on the slot processing time. Why it's speculative? Because these numbers are probably not that accurate, but the main what is to highlight here is that it's highly likely that Eth1 processing time will differ from the beacon block processing time by an order of magnitude. So let's just assume that these numbers are correct. We have like 3 to 6 times increase in the producing, propagating, and processing the block by the entire network. And what's to pay attention here is that we should be we have to do all these 3 parts of the block dissemination, like within the first third of a slot, to allow testers to attest to the most recent produced block. And if we take these numbers, we see like 30% increase, 30% increase, 25% increase of this time, but it's just a 30% of the whole 4 seconds, which are dedicated to this first part of the network activity in each slot. And even if we say that Eth1 block processing will take 1 second, and beacon block processing will take like 100 milliseconds, and we increase the propagation time up to like 500 milliseconds, which should be pretty fine, and we will have like slightly less than a half of this portion, this first third of a slot time in advance. So what's to improve here? Probably the potential option is to process Eth1 block and beacon block operations in parallel, but this is not of a much gain here, and it's up to client optimization. It's up to client to decide on this kind of optimization, and probably it will make more sense when the relation between numbers will be changed. So
something important to note on the first 500 milliseconds you have in there is the block production, right?
Yeah.
So as a proposer, I can probably in most cases actually opportunistically compute and process my block prior to the start of my slot and broadcast immediately at the start of the slot. And so I think we can, with the right optimizations, which I think Nimbus and others have been doing such optimizations kind of in the context of epoch processing, I think you can probably cut this in half in most cases.
Yeah, right.
Always, if it's as long as the previous block is available, right?
Right, and even with the fork choice fix that we're putting in mid-year with like kind of the adherence to the vote of emptiness, it even becomes better there because you don't get that late block throwing you off like right before the beginning of your slot.
Yep.
What happens if we exceed this limit, if it takes more than 4 seconds?
Likely, testers are not going to see it on time, and they're going to say nothing happened, and you're going to be orphaned.
Yeah, it sounds pretty bad.
Yep.
Yeah, I mean, it's something that you would expect to happen from time to time, but that you would, is like a huge optimization target, something that if you're writing a client, you don't really want to see.
Yeah, by the way, I have like a quick question to client implementers on the front side. What is the Eth1 block processing time at the moment on average machine? Do you have any intuition in that?
About 100 to 200 milliseconds.
Nice.
Yeah, cool. Okay.
The other aspect of this is the network propagation in terms of what validations you have to do before you gossip on a block. In Eth1, you just check proof of work. You don't execute the transactions. Are we able to do the same kind of thing with the beacon chain? Basically propagate the Eth1 block assuming it's valid?
Yep. I think we'll just do what we do currently on the beacon chain, just verify the signature, the proposer. Is this what it does currently?
Yeah. The proposer signature kind of does a similar thing as the proof of work in that it's expensive to create a proposer signature, and definitely to create multiple of them. And so you assume that there's validity behind that and just propagate it on. Similar to proof of work.
I just wanted to ask a question. This wasn't entirely clear to me. With the Eth1 data being propagated as part of the beacon chain, and then with this execution happening for validators, am I correct to believe that all beacon chain validators, which means all Eth2 validators, will now have to propagate as well as execute the Eth1 blocks, or is it is there some subset self-selection or something?
In this design, it's like, as you said, every validator will execute Eth1 block and propagate it into within the beacon block. It's just actually part of the beacon block. It becomes a part.
Okay. So then I should think of the ETH1 data as being 64 times more expensive because versus shard data.
64.
Just in terms of the fact that it's not just being done on one shard, it's being done by all validators.
I don't actually get this.
Yeah, I don't know. I mean, maybe the supply and demand of what is essentially like the ETH1 payload versus sharded data, those would be independent. So you might expect data to be very much cheaper on those shards rather than where you're competing for execution and shard and state, kind of an ETH1 land. But I don't know if, I don't have an intuition for whether there'd be like this like kind of 64 mapping because there's less amount of validators doing work on the other. I don't know. Does anyone else have an intuition there?
Yeah, sorry. The way I asked that made it sound more like a financial question. I originally was actually just thinking about it from computation, bandwidth, storage, those types of like resource.
Yeah, it's being done by all the validators, and which presumably is not. I know that some people are using Infura, but presumably not like an increase in load over what is today. Obviously, if you get stateless Ethereum, and if you do the design of moving this out into a shard, which I think most decisions are being made in the design so that that it can facilitate such a movement, then you could have reduce the requirements there. But also I mentioned statelessness. Statelessness isn't required necessarily to move it out to a shard, but it's required to then have multiple instances of state and execution, because if you don't have statelessness, now you have the burden of 2 states or in states, however many shards you make.
Well, I would claim it's a fake shard if it's not stateless, because everyone has to validate it. So how is that a shard?
Right. You could check it in, but you can't. You could check it in as like the data was available, but you couldn't actually do the execution. You're right, sorry.
Even that would require being able to construct fault proofs.
Right.
Okay.
Yeah, so I mean, this design pretty much elevates what we call ETH1 to be a first-class citizen, live right next to the consensus, and facilitate an early merge. Given how sharding develops and how it's used inside of this like ETH1 and statelessness and other moving parts, you could imagine moving it out from the beacon chain and kind of reducing the load on consensus participants. But there's a lot of different moving parts there.
Okay, cool. Let's just move to the last slide, which summarizes the Eth1+Eth2 communication protocol. There is like the third method here, which notifies the Eth1 engine about the block is being finalized, and allows Eth1 engine to do the garbage collection at this point. So that's all with regard to the communication on the system layer. Yeah, there will be definitely some extensions in the user level JSON RPC, but it's like decided on the concrete design later. So unless there are any more questions for the ETH2 part, I would like to turn over to Guillaume, who will proceed with the ETH1 side of the deal.
I did have just a thought about how during the, I guess, per block processing, we have to call out to Eth1. It seems like that during syncing, that the latency times would start to be pretty significant there. I wonder if some sort of batch verification would be useful.
What latency do you exactly referring to?
So just like, because before, say, process block there was this pure function and we've all been optimizing it, shaving milliseconds off it. And then process executable data is now a JSON RPC call. There's going to be a bit of latency there.
You mean the latency for the call itself, or the whole processing cycle?
I guess the computation is going to be a lag as well, but it seems like a necessary lag. But the HTTP call there seems like it's going to add some slowness to it. So I'm thinking perhaps it'd be nice if we could say, like, here's 64 or 128 blocks. You go and verify them and then come back to me when you're done.
Oh yeah, I see what it means. So it's like deferred execution, right? I mean, so you process the beacon block, but you're deferring the Eth1 execution for like some time, right?
Yeah, that's right. You can kind of like do them in parallel in a batch and remove, like, divide the HTTP overhead by like 64 or 128.
Yeah, I see. But since the Eth1 execution can invalidate the beacon block, like, it's probably not the best strategy to do it that way.
Yeah, I mean, I guess it's not a good strategy if you're on a network that's like serving you bad finalized blocks, but I hadn't seen that one before on Eth2. I think being optimistic there is probably a big win.
Yeah, and this is probably a good strategy for like the sync process. So you just execute the beacon block, you get to the top of the chain, and then you can process like Eth1 blocks in parallel and finalize like this.
Nice.
Probably start process Eth1 blocks from not from some finalized checkpoint only that's been discussed. I mean, to skip some execution during the sync process. Yeah, but if you're like syncing, if you're catching the head and staying in sync with staying online, staying in sync with the network, you probably want to like execute one by one sequential order.
I agree.
Yeah, the process of fast sync probably comes in here when you're talking finalized. You don't want to have to do a full sync of the entire mainnet of Ethereum because it'll take you days to catch up. Right. So you're probably looking at just ignoring processing these Eth1 engine blocks and letting it fast sync the world state up to something close to head, and then you hopefully just have the non-finalized, and hopefully something faster than fast sync by the time we get around to there. I know there's a few different proposals, but
I mean, the requirement for synchronous execution here also implies that the outcome of the Eth1 block production call depends on the data that you pass in there. So when you're syncing, basically you need to execute the Eth1 block in that historical context.
Right. And I would say oftentimes you're maybe not actually executing that Eth1 context and more of like doing some sort of fast sync with respect to the Eth1 state and then doing a snap sync or something like that from there. But there's definitely a lot of trade-offs in sync speeds and computation and what's optimistic and parallelized and things. Okay, thank you, Mikhail. Let's turn it over to Guillaume.
Thank you.
All right, thanks. Let me just share my screen. So I'm split between two computers. Can you see the screen? Yeah. Okay.
Yep.
Cool. Yeah. So I've been asked to talk a bit about the changes I made to Geth to create this thing called Catalyst, which is an Eth1 engine, and try to explain to you a bit what changes are involved in order to build either to interface with it or to build something similar. Yeah, so it's not so much a talk about what I built as a talk about what I broke. The idea is we took this very closely like designed, very well designed piece of software, and we I just ripped apart all all the bits that were not needed. So like the goal was to take something that works and try to build a prototype to see where we were targeting. Yeah, try to understand where we were going and build it. Yeah, like Mikhail said, we have this structure, and you can see that most of the components in there are basically what you would find in a block. So when you ask a block to be produced, an Eth1 block to be produced, this is what you get. And there are things like the difficulty, which are still currently remain, and that's basically what this talk is really about. There's a lot of stuff left in Catalyst that still inherit from Geth, and that will slowly be phased out. But the idea is to just get something pretty pragmatic, get something to work. Done is better than perfect, and then slowly make it more streamlined, more release like production ready. So the changes I've made so far into Geth to obtain Catalyst is to deactivate block reception at the protocol level. So Catalyst is still connected to an Eth1 network, so a DevP2P Eth1 network to receive transactions, but we don't want to receive blocks. Blocks are passed from the Eth2 into JSON RPC interface. Then I added some the RPC calls for the connection. So this is how we were able to build the demo that Mikhail did a few months back. And I added some instruction. I mean, at least currently just one, to get the root of the beacon block. So like you can get the up to 256 blocks past beacon block routes in order to try to access proofs and fields of the beacon root from an EVM contract. So the block production, on the block production side, I mean, it's been covered by Mikhail, so I'm not gonna dwell too much into this. But the idea is that you just get the parent hash, so you know where you want to insert your block. So it doesn't have to be on the canonical chain. There's a bit of a problem with this that I will cover later. But otherwise, it's all the info you need to produce a block, and then you return like the call returns executable data, and then you have when the block is produced, it's then propagated on the Eth2 network, received, unpacked, and the validators call their own version of Catalyst with the same executable data. So compared to the block production, the parent hash has been lost because it's currently in the executable data, but otherwise all those informations could be accessed from an EVM contract, so they need to be accessible. Like they need to be the same as when they got produced. So I currently added this instruction that I set in the same space as all the other let's say execution context instructions, like guess limit, like block hash, and I arbitrarily decided to give it the same cost as block hash. This is not something that was really discussed. This is a choice I made because the code for that looks a lot like that of block hash, so I just gave it the same cost. And yeah, this is a temporary decision. It's not set in stone. The idea is that the block hash will probably be replaced by a beacon block root in the future. Yeah, so just to summarize this first part, there were a few challenges in creating this thing that people who want to make their own Eth1 engine might be interested in. And it's basically the fact that when you insert a block, you might not insert it on the canonical branch. So at least from the view of Catalyst. So there can be a reorg, like all the difficulty management is still present in there at the moment. And so there might be a reorg. And so far we try to make sure it's it's not like it's contained and it will be phased out. But yeah, that's something we like I kept around for the moment, because this is a very, very intricate code that has been honed over the years, and we don't want to touch it before knowing where we're going, and to make sure that we can proceed. Yeah, another important thing is that Guess doesn't really support the ability to have block numbers that have spaces, like missing block numbers, like the parent of a block needs to be the same block number -1. So if you miss slots, if slots are missed, the block, like the Eth2 engine needs to make sure that whatever reference to the block number will be continuous, and otherwise Catalyst still has all the same all the features or problems connected to difficulty. So the difficulty bomb still exists. There's if you set the wrong kind of difficulty, it will try to adapt. So the timing might be off. So there's a few gotchas to be careful with at the moment, if you want to play with Catalyst, or if you want to just do your own version of it. So yeah, that's just wanted to make sure. Yeah, is there yeah. I was told to ask if there were questions. So if you have questions, otherwise, okay, I'll proceed. Right. So the upcoming changes, there are a few things like that are going to come to ETH1 that are necessary, like the ability to read the BLS signatures to handle binary trees. So all these things are on the way. Now the question is, are they going to happen before the merge or not? So that's a big question mark. We're trying to not count too much on that. So it could be that there will still be hexary trees after the merge, but I think BLS is kind of a requirement. So there are some discussions for that. So yeah, we would have to wait for that to happen. Right. So far the tests I've written are mostly Go, like simple Go tests. We have written in the Go test framework. We want to use something called Hive to do those tests. So that's what's gonna keep me busy in the next few weeks. And of course, there's testing the merge. So the merge has been tested technically in those unit tests. But yeah, I think we should before we start building a whole test net, I would like to validate more worst case scenarios, more questions that I have, and this is what Hive is going to be.
That's the actual point of the merge, swapping from proof of work at one instant to the beacon chain at the other.
Right. Yes. So yeah, I mean, okay, exactly. But that's what I think should be tested more. At least that's where I'm not so comfortable giving the go for like, if you ask me, is the merge happening tomorrow? I would say, well, maybe maybe first try to test it a bit more. So yeah, that's what I was getting at. And then there's the question of the sync. So the sync is how do you synchronize a Catalyst client after the merge happen? A lot of things are going to change, so it's going to be a bit difficult to at least it's not straightforward to synchronize. So that's something that's still being discussed, and yeah, that's I mean, I'm gonna go over those things. So Hive was it's a test environment we've got, so it's nice because it's Docker based. So if you want to play with Catalyst, you can just create your own image. So Hive at the moment doesn't really support Eth2 clients, but this is something Proto wanted to look into. So yeah, we're going to work on that. So in our team it's Rene and Felix who work on that. So it's nice to see some interest on this side of the Eth2 of the research team, and we're gonna try to make those those two things work together so that we can test the merge and get some proper data and find the obvious bugs before we start the testnet. So when it comes to the merge code itself, well, it's basically like any other fork. You wait for a given block, and after this block, you start activating, like you change the behavior of Geth or Catalyst. The only problem I would say is that it's not exactly a problem, but you're going to have to disable difficulty and block ceiling, and those two things are quite subtle and quite like difficult to handle. So like we're pretty touchy about changing the consensus, for example. So this is something we're gonna have to look into fairly carefully. And yeah, the last part is about the synchronization. So there are really two methods that I can envision. It's still something that we are thinking of in the guest team. So we're still I mean, at least I'm still thinking about it. But there are 2 points. There are two possibilities. Either you ask the Eth2 client to provide you with the actual blocks, so you let the client figure out which blocks are correct and insert them. So that's nice for me because I don't really have too much work to do. The problem is that you don't really understand, like you're not able to verify because you have this finalization, and presumably after the finalization, everything that comes before is garbage collected, is destroyed. So you can't really have this property that you can synchronize all the way from the beginning and verify and re-perform the merge afterwards and check everything went well. So an idea that Peter proposed was, since we know what is the last finalized block, you could download the header chain backward. So you download the block, you check what was the parent, you ask for this one because you know this one, this finalized block is official, so, or at least is finalized. So you can find your way all the way to the genesis, and then you can download the block bodies either from IPFS or from other clients. That's something that is going to require, at least that's what Peter was saying, some significant tweaks to the downloader. So it's not as easy, but it's got this nice property that you can actually check from the start. And the other aspect of the sync is, of course, how do you sync the state? So there's this problem with that exists already in with the fast sync. You download the state, but by the time you're done downloading the state, all that data is like what the guest client does. It only keeps, if I remember correctly, 256 states, like the state for the last 256 blocks, and then afterward this gets deleted. So you find yourself having to download the data, and then by the time you're done downloading, or in fact before you're done downloading, the machine or the node you're downloading from has already moved on and deleted all its data. So you find yourself having to catch up, and that can last actually a lot of time. So there's this new synchronization algorithm that mostly Peter and Martin have been working on, which is called the snap sync, and provides much better results and much better performance. So we want to try that, and at least to download the data. So that's what we're thinking of at the moment. And yeah, if you have any questions, if you want to play with Catalyst, you can ping me on Discord. I'm on most servers, and yeah, this is the name of the branch that contains I would say not the most up-to-date version, because there will be a new one published in the coming weeks once I'm done playing with Hive. Yeah, this one is the one that was built for the demo. So if you want to have a look, if you have questions, this is where to look. And yeah, that's pretty much it for me.
I have a small, not necessarily question, maybe addition and question. With regard to synchronization, Guillaume mentioned that there are kind of two approaches. One of them is to just rely on the Ethereum 2 client to figure everything out and then just feed the blocks to the ETH1 client. This is super simple from our perspective. Unfortunately, the reason I don't think this is feasible is because, well, first thing first, do the pruning in ETH2, the chain pruning. But the bigger problem is that an ETH2 client wasn't really, I mean, the ETH2 client doesn't have the necessary code to streamline the data that we want in our little ideal conditions. So for example, depending on whether we're doing fast sync, or normal syncs, we do a lot of things concurrently. We download headers in advance with gaps in them and then backfill them. We concurrently download block receipts, block bodies. We store some of them in LevelDB. We store others in flat files. And essentially we have this super complex logic where we try to somehow get everything into their right places on disk. And the problem is that if we rely on Ethereum 2 to feed us this data, then, I mean, Ethereum 2 won't implement all this insane complexity just because Geth wants it. So it will be a huge step back performance-wise, sync performance-wise. That is why we're saying that we would, I personally, I only see it working, at least downloading historical states only if Geth can download it from other Geth nodes without needing to reach out to ETH2. And in theory, we can do that if we know the header, I mean the hash of the head block. Then based on the hash, we can download everything backwards because everything is cryptographically proven, so to say. The catch, which I realized today, is that if we want to include these extra context store fields from Ethereum 2, like these rundown numbers or whatever else. So everything that we need to introduce, that we want to expose from Ethereum 2 into Ethereum 1, those need to be packaged up in the Ethereum 1 block. I mean, it somehow needs to be retrievable by the Geth nodes during sync. Otherwise, Geth again relies on ETH2 to have them. So this is an interesting limitation. I would say that it's probably not that hard to do if we allow ETH1 blocks to be extended with the necessary extra context. And I mean, ETH1 already has a timestamp, which is just a random number. It's fine to add roundao and other random numbers too. Just saying that, in my opinion, probably relying on the ETH1 clients to synchronize the ETH1 blocks is the way to go.
Yeah, I see that. And I see how you could take some of those things and add them essentially to like the header payload or something else as the payload. So it's kind of embedded in that ETH1 hash for consensus. I do wonder what sync can look like in the context of finality and weak subjectivity, assuming a user shows up with some finalized root, which would presumably have the finalized like ETH1 block hash in there. What historic sync is requisite there, other than just saying, give me the state, maybe in some fast sync or snapshot sync, and let me compute from there forward? What is I know it might be nice to have in backfilling everything, but what is requisite there?
Well, first up, if you say that, hey, give me the state for this finalized block, that won't ever happen. So Ethereum 1 nodes currently prune blocks older than 128, which is approximately 15 minutes.
Gotcha.
So anything that's older, any state that's older than 50 minutes, you can forget about it. So the way synchronization can work is that if you give me, for example, your current head block or the finality block. No, actually, I need your current head block. So, so currently, what the Ethereum 1 chain does is that we request the head, and we retrieve the state from the head minus 64, give or take, block, which is still available in the network. And then when we finished up syncing the state, we have a fairly recent block, but not very, very recent. And then we start computing from there. And the reason why we prefer this almost recent block is because if there are these mini reorgs, then we still have the state to go back to and calculate on a different fork. Now in Ethereum 2, I'm not exactly sure how many blocks, so when finality occurs, how many blocks we have to process until it hits. So we can definitely play around with this 128 number.
Right.
But in general, it's state in Ethereum consumes a lot of memory. So the more state you want to maintain in memory, the more memory you need, kind of.
Mm-hmm. So two opportunities. If say I give something to the Eth1 engine that's 2 weeks old, the Eth1 engine then could go forward in time. You don't need to go back in time from there, right? You can go forward in time to block sync, header sync, and then state sync from there, correct?
Yes. So the thing is that as long as data is available in the Eth2 client, and I can always ask for it. So you can give me that, hey, this is the hash of the finalized block, and then backwards I can just use the Geth network to retrieve all the historical state or however much I want, and then I can go forward. But every time, so in Ethereum 1, the only way I can go forward is by checking the proof of work. So kind of the proof of work is the thing that allows me to go forward. Now, if we nuke the proof of work and we replace it with the proof of stake, then it means that I need to ask somebody whether a block that I received from the network is correct or not. So I need the Ethereum 2 client to tell me that, yes, this is the next block, yes, this is the next block, yes, this is the next block.
Right.
So that way it is perfectly possible to go forward to yes.
So and then the alternative is the Ethereum 2 client tells you essentially the ETH1 head. What can you do from that?
So if I have the ETH1 head, I can download everything else backwards, as long as all the context is available. So that's why I was saying that we would need to add all these ETH2 fields that you want to expose into the EVM. Those would somehow need to be bubbled into the ETH1 header, so that those become part of the ETH1 history.
Do we need to download anything else than the most recent 256 blocks to serve the block hash opcode? I mean, in terms of the history for ETH1.
Well, the state.
Yeah. I mean, the history blocks.
But presuming if you have the head state.
We don't even need the full blocks, only the headers. The 256 headers.
Oh, yeah. Right.
So
you need the head state and the 256 headers.
Right, yeah.
Yeah, so here there's an interesting, so here we're kind of going into a theoretical problem. So practically, no, you don't need anything else. The theoretical problem is that currently Ethereum guarantees that you have the chain and you can always rerun the entire thing. Now, if we want to do a merge from Ethereum 1 to Ethereum 2, the question is, do we want to immediately break this promise and just nuke out all past history or not? I would say that it's a bit strong to nuke it out immediately. My personal suggestion would be to maybe launch, have ETH1 as one shard and have multiple other EVM shards which don't have historical states. So there you could say that you're willing to nuke out all states older than, say, 256 blocks. And eventually when people are used to this model, then maybe then you could remove history from ETH1. But I guess my main issue is I also mentioned this to Guillaume, that if you're going to merge ETH1 into ETH2 and simultaneously just nuke all the history, then that will be a fairly large, I would say there will be a fairly large opposition from the current.
What do you mean by nuking the history?
Well, if I'm not maintaining all the blocks, blocks older than 256, then essentially that disappears from the network.
Because the key thing there is that those block headers link to the log events as well. So when contracts emit logs, there's a lot of dApps that then depend on that history and having the full chain history there. Is that right?
Yes, I haven't thought about that, but yes, that is also right.
So you're actually concerned specifically about the blocks and just that replayability, like the re-verifying the chain, not just the data.
But why would we ever lose that? I mean, it's a pure, like, we have to have the capability to like a weak subjectivity thing. But you can always replay all the blocks from the start.
Yeah, but you have to store them somewhere, and if you flush them out from the network, then where are you going to get them back from?
Wait, but does the ETH1 history, like, aside from the dApp and the log use case, is there any valid, like, is it just like a museum essentially? Like why would regular consensus nodes need to care?
No, that's what I'm saying. They don't need to care, but that's a current invariant of the system that we need to be. We can break it. There's no technical reason why we shouldn't break it. It's just a social reason, so to say.
Right.
It's definitely a social layer consideration there.
But I mean, you can just, I mean, anyone can just store this history forever. Like having the peer-to-peer network have to store it seems like a very useless requirement.
Well, I mean, anyone can store the entire history of the internet, yet the Internet Archive has a fairly hard task at doing it. So the thing is that...
I get it. Like it's like just continuing to run the current equivalent of an archive node. If we define that as being archiving the pre-merge ETH1 would require explicit work if we want that functionality to continue existing.
No. I mean, you can always do it, right? I mean, you can always be your own archive node. The question is, I understood as, does the peer-to-peer network support you getting all the historical state becoming an archive node, right?
Right.
And that's the question. That I really wonder if that is really required, and why not use BitTorrent for it instead.
Wow. So one interesting issue here is that with an archive node, currently, if you want to run an archive node, then you can rebuild it from the network, from the full nodes. But if we were to stop the Ethereum network from maintaining the chain history, then you will not be able to rebuild it from the Ethereum network. You would need to find some third-party source. Again, this is from Ethereum's network's health perspective. This is fine. You don't need the history. It's just a social promise that we can break. Just we need to be perfectly clear that we're breaking it.
Break it with intention if it is to be broken.
There was this idea to store. There was this idea to store the blocks inside the storage tree. Is that would that solve the problem?
Why would that be a good thing?
Well, okay, it would be a bad thing because we would increase the size of the state. But at the same time, if you go back in history, you have all the previous blocks stored in your state.
Yeah, well, might as well just keep it stored the way as they are.
Yeah, and you essentially have that just through the nature of it being blockchained. Everything's committed to, at least in a similar way to state.
Maybe another comment on this, does the network provide history thing? isn't it already the case that yes, like it happens to be default behavior, but nobody is actually incentivized to actually have the history. Like I could easily change my node to not have the history right now, and I would suffer no downsides, right?
Yeah, and there are clients that do that.
Other nodes
So in
typically disconnect from you.
Sorry? What was that?
Ditching the history is generally probably viable, but you might have issues maintaining certain peer connections if your node is unable to respond to requests, right?
Right.
But
So,
the
but
only
you
peers that
basically
would be
you lose the peers that are currently syncing, which aren't doing much for you anyway. Is that?
But the thing here is that currently most nodes assume that most other nodes play nice, and there's no reason to add extra protective mechanisms. But deleting chain history is essentially you become a leecher of the network. You just gather the data and you don't give anything back. And if more and more people start using that, then probably clients will start adding protective mechanisms to try to filter that out. And it just boils down to this war between clients of trying to somehow get away with leeching as much data as possible.
Right, but I disagree here because the node is still a full peer-to-peer node in terms of relaying blocks, providing recent history even. It's only...
You're essentially a live client, or okay, not live client, you do have the state, but you're not a... If you don't have the history, then nobody else can sync from you. So...
Yeah.
So you cannot help others get onto the
network. This is the philosophical question whether it actually is important to sync from
if that's how users expect to be able to sync, which might in fact begin to change in this notion of like having finality and weak subjectivity, but definitely some like sensitive things to consider when we're dealing with thinking about the still relatively undefined component of how to do sync in this context. We're 15 minutes over. I think we're gonna end it here. I really appreciate everyone showing up today. Thank you all the speakers. That was super informative. I'm glad this is on YouTube so people can learn and begin to collaborate more. As you know, if you took anything away from here, there's plenty of work to do. There's definitely some like concrete foundations all around. There's beginning to be things that look like specs, but there is a lot of work to do. And there's been a kind of a small group working on these things as the Beacon Chain was launched, and as always, Eth1+X is maintained, but it's time to dig in deep on all these elements. So as always, generally collaborating in the ETH Discord. There's the E2 call, although that's more like kind of just us checking in on things. We might think about how to restructure that in the context of some of these R&D things, or have some smaller breakout calls and stuff. Other than that, thank you Xiaowei for organizing this, and again, thank you everyone for taking the time. I know it was a little bit long.
Thanks everybody.
Thank you.
Thank you.
Thanks.
See you all in person one day. I promise.
Yeah.
Bye.
Bye.
Muskoka was a good place.
Bye.
It was indeed.
Yeah.